Okay, good afternoon, everyone. Let's welcome Professor Shrivastava from IIT Bombay, Mechanical Engineering, for today's Sabarmati Young Researchers Seminar Series. Amber has done his bachelor's from Marine Engineering
Engineering and
and
Research
bachelor's in
Institute.
Marine Engineering at Marine Engineering and Research Institute, Calcutta, and then he did his master's from Idaho State University in US, again mechanical engineering. Then he did his PhD from Wisconsin Medicine in mechanical engineering. Amber's research area is mostly friction stir welding uh, from the mechanical engineering and material science point of view. And today we are going to talk about mostly flaw detection or in-process discontinuity detection in friction stir welding. So let's welcome Professor Amber Shrivastava.
Good.
Thank you.
Thank you, Amit, for the brief introduction, and thank you all for joining us for this talk today. Today, I will focus on in-process discontinuity detection during friction stir welding. So the term discontinuity here essentially is any defect which forms during the welding process. It's a more industrially acceptable term, and it's a group of different type of defects. It can be a tunnel defect on the advancing side, which is very common during friction stir welding. There are defects which are focused primarily at the root of the weld. Those kind of defects would also fall under the category of discontinuity. There can be pores, porosities, as all of us are aware of. For case of fusion welding, lack of fusion is another complicated defect which forms is not easy to detect. All those defects are put together called as discontinuity. And the idea of this project when I was working on this was to be able to detect these defects for the case of friction stir welding during the process itself. So we will start with why we need a discontinuity detection method or methodology for the case of friction stir welding particularly. And then is it feasible to detect defects using force signatures? We need some parameter to be measured, and by looking at the variations in that parameter, maybe if we understand the physics of the process enough and see the correlation between the parameter we are measuring versus the defects, maybe we can detect those defects during the process, right? So a preliminary force model, and then based on the limitations which appear from that preliminary force model, we would be able to see what further needed to be understood. How we move forward, it appeared very early in this project on this work that we needed to understand what's the morphology of these discontinuities are and how these defects are or discontinuities are forming during the process. Further upon, based on the understanding built during the project, we proposed a discontinuity detection method which not only could distinguish between a good weld, i.e. weld without discontinuity and weld with discontinuity, but also could give us a fair estimation of the size of the defect or discontinuity which is formed. Finally, additional work was done to validate the method which was developed. Um, Apparently, most of you are familiar with friction stir welding. So without spending too much time, it's a solid state joining process, relies heavily on the plastic deformation of the material, and uses primarily no filler material. And then once the material is heated, primarily due to friction and plastic deformation, heat dissipated due to plastic deformation, the plasticized material flows around the rotating tool and material from the two workpieces join together. I will quickly show a quick video and I hope it runs here. So here we see a non-consumable tool which is rotating at certain RPM and is plunging into the workpiece. There are two workpieces, aluminum plates. The tool is going to plunge till a desired depth is achieved and then it starts moving at the seam along the travel direction. So a lot of you would have seen a similar process. And what happens here is, as the material is moving, material from both the plates is plastically deforming and basically flowing like in its plastic state around the tool which is rotating. Eventually, once the whole weld length is achieved, tool is going to deplunge and move back in the vertical axis, and we have a fully consolidated, hopefully a fully consolidated joint in place. So moving forward, the process friction stir welding has a lot of inherent advantages over conventional welding processes. If we ignore the huge initial capital investment which goes into this process is essentially less expensive than conventional processes because of lack of any filler materials, lack of any shielding gas which is required. And if we are making bulk welds, a lot of welds with this process, soon the capital cost will also be offset. Besides that, a lower amount of energy is consumed during the process because there is no melting which is taking place. And during fusion welding processes, there is certain amount of energy goes in bringing the material up to the melting point, and then material has to melt where it absorbs the latent heat, and it's a large component of the overall energy consumption during the process. Since friction stir welding is a solid state joining technique, there is the energy consumption is much less as compared to the traditional techniques. Fewer pre and post processes. As you saw, there was no special V groove or U groove was developed in the demonstration I showed earlier. And that's a very good example of how pre-processes are lesser required for the case of friction stir welding. Major advantages, as some of you, Professor Arora told me earlier, are working in the area of joining dissimilar materials, which is not as feasible or as easily possible with the conventional welding processes or fusion welding processes. Despite all of these, and because of all of these advantages, this process is getting readily accepted into a lot of high reliability application areas where the initial capital cost is justifiable, like aerospace, marine industry, transportation industry. However, for such high reliability areas, one major requirement is also the post-weld inspection. And a lot of cost, time and effort goes into the post-weld inspection. Are there any defects in the weld? And if there are those defects within a prescribed limit? They should not be more than a certain critical value, otherwise the weld will be deemed unusable. So because of these reasons, the in-process discontinuity detection, if it is possible to detect defects which are formed during the process itself, becomes very helpful because it will end up saving a lot of time, money of course, and then making this possible far more easily acceptable to the industry, where all of its inherent advantages can be exploited. So that brings us to the objectives of this work when I took it up, was to develop a discontinuity detection, in-process discontinuity detection method for friction stir welding. Then to not only predict if a defect is formed, but also if possible to estimate the size. And in order to estimate the size, one had to look into how the defects are formed, what's the formation mechanism, then what is the relationship between the discontinuity size and the parameter which you would be measuring. In this case, I chose forces for a lot of reasons which will come down later. And then of course to be able to precisely with very high resolution measure the forces, real time measurement of forces during the process. So coming on to the subject of interest here, a quick look at the existing work performed by previous researchers very clearly indicates that during friction stir welding, material moves in two different regimes. There is an upper lobe and there is a bottom lobe. The upper lobe is primarily the material which is moving under the influence of the shoulder. The tool has a pin at the bottom and a big diameter shoulder. The shoulder is completely in contact with the top surface, while pin is the one which protrudes into the workpiece at the seam. So there is a distant chunk of material which is moving under the influence of the shoulder, and then there is a material which is moving under the influence of the pin. So it has also been very clearly identified by various previous researchers experimentally, particularly post-weld kind of characterization techniques have shown that the material under shoulder primarily moves in a very continuous fashion. Material keep on coming in, moves around, deposits, keep on coming in, moves around and deposit. And there is no interference, there is no cyclicity involved, periodicity involved in the material movement. However, the material under the effect of the pin moves in a very periodic fashion. And this periodicity of a particular nature, and we will see that the experimental work from this project also reveals or substantiates this periodicity, where we hypothesize, and eventually the experiments also strongly suggest that a cavity forms once per revolution behind the tool, and this cavity gets filled by the incoming material with the effect of the material moving under the influence of pin. And this cavity opening and filling once per revolution gives a very cyclic nature of the to the material flow. Now, this same cyclic nature of material flow or periodicity is very well reflected in the force signals. So, for most of the researchers who have performed high resolution force measurements, they see a lot of periodic force variation at the frequency same as tool rotation frequency, because the cavity is forming once per revolution and getting filled. So, you will see one spike and one trough, and then again a spike and then again a trough in a revolution, and forces oscillate at the tool rotation frequency. So, in order to see feasibility of force-based discontinuity detection technique, a very crude model was proposed initially, which says that the force is proportional to the amount of volume which is moving under the influence of shoulder or pin. So, Fs is the force moving under due to the material which is moving under the influence of shoulder, and Vs is the volume of the material which is moving under the influence of the shoulder. Same thing for material which is moving under the influence of pin, and the forces which are generated in driving the material under the influence of the pin. And a constant of proportionality was introduced. Now, in order to identify a value for this K from work which was done by my predecessor, a lot of experimental work he did, we took up a bunch of data and we identified a set of good welds and bad welds, because bad welds we want to ignore. Bad welds are those which have discontinuities in those. So, we defined a line of say UTS above 75% of parent metal, and the welds for which temperature did not cross melting point of the base material, because melting point determines if the material melted or not, and in this process we do not want the material to melt, because a lot of its inherent advantages are coming from the fact that that the process is a solid state joining process. So, once the good welds were identified, we went ahead and calculated theoretically what's the volume of material which is driven by the influence of the pin. Essentially, the material which is in thickness equal to the APR, advance per revolution, and in length equals to, so it's an annular cavity or annular space of material whose height is same as the pin height and thickness is same as the advance per revolution during the process. And then the force amplitude was determined from the forces which were measured during the process. A ratio of those gave us a constant, and this constant was averaged for all the good welds, and it was identified that 10.8 newtons per millimeter cube of forces is required to move the material, and there was a standard deviation of 2 newtons, which looks pretty big to begin with. However, this is not the final model. The objective was just to see if we couple a model like this with a control theory based disturbance observer, can we predict the formation of defects and their sizes in real time. For these forces, we had the force signal, and we will see in a bit how the forces varied. But some of the very interesting observations and inferences came when we did the Fourier transform of the force signatures. We could see very distinct peaks at the tool rotation frequency, 18.3 hertz. This weld was performed with a tool which had 3 flats on the probe or the pin. And this was performed at the conditions which was known to produce no discontinuities, no defects in it. And you can see there is one large single peak at the tool rotation frequency, and there are minor peaks at the higher harmonics, 18.3 into 2, 18.3 into 3, so forth and so on. On the other hand, for the welds in which discontinuities were known to occur or were present, we could see additional peaks very clearly at a particular higher harmonic which corresponded to the number of flats on the tool itself. For example, this weld for which we knew there are defects, and when we did the fast Fourier transform of the forces, we could see not only a large peak of force at the fundamental frequency at the tool rotation frequency, but at a frequency which was 2 times, and 2 comes from the number of flats, 2 times the fundamental frequency. Same thing here, we could see a relatively larger peak at a frequency which was 3 times, and 3 corresponds to the number of flats on the tool probe. So these observations were built into the initial model. So any oscillating signal has 2 components, a DC component and an AC component. So DC component, as we have already said, material is moving continuously around the shoulder, is believed to primarily come from the continuous motion of the material around the tool. So material is continuously moving, and this bulk of material has to move with respect to this axis from minus pi by 2 to plus pi by 2 rotation. And for this center of mass movement of pi by 8, we can see a static signal. And then for the pin driven material at any given location theta, which can be represented at omega t, so at any given time we could get an expression here which will capture the cyclic nature of the force variation. Combining these 2 static and oscillating components gives us a force model, very crude force model, but would allow us to apply controls theory to it and to see from in process, during the process, from live force signatures, can we detect defects or not. One thing to be kept in mind, at this stage, this model does not account for any defects which would have been formed. So the question comes how to account for those defects, right? So this is where the additional dynamics which I talked about in the previous slide comes into the picture. So let us assume that the size of the defect is Vd, volume of the size of the defect which is formed is Vd. And we also know that because the cavities are formed in the pin-driven region, the defects are primarily forming in the pin-driven region. So what we can do is we can reduce the size of volume-driven material from the pin-driven, size of the defect from the pin-driven material itself, and then add a term for the additional dynamics which will occur at n omega t. So this term here captures the force dynamics which is happening at the tool rotation frequency, and in case a defect is formed, if Vd is 0, this term disappears, but if there is a defect which is being formed, you have additional dynamics which is occurring at a frequency which is corresponding to the number of flats on the probe. Now comes the question, why this phase difference? So with respect to our axis x, most common type of defects which are forming during friction stir welding are on the advancing side, and with respect to the x-axis there is a phase lag of pi, and with respect to y-axis there is a phase lag of 3 pi by 2, and that gives us a complete model for which the only constant is k. Vp can be calculated theoretically the way I mentioned before. Vd is going to be the outcome given forces are measured or known in this model. So a discontinuity observer was established. What in controls theory, what does an observer do? Observer essentially simulates the process model, the model which we just established, in parallel to the actual physical process. Friction stir welding is happening and we are measuring the forces, inputting it to a computer. Computer itself, using its own processor, is simulating the process in real time, and in real time it is comparing the signals which is coming from its own calculations and coming from the physical measurements. It compares those 2 signals and feeds it back through this discontinuity observer to spit out an estimate of the size of the discontinuity. Now what's the objective of the observer is? Objective here is to take this size of discontinuity, substitute it to the process again so that this error can be minimized. As an observer mathematically tries to minimize this error, its prediction of the size of the discontinuity becomes closer to the real size of the defect which would have been formed. So in order to test or to see if it is feasible to measure or estimate defects or discontinuities which are forming using such a methodology or not, we performed some of the welds at some of the representative conditions where we knew that the weld number 1 produces weld without discontinuity and remaining 2 welds are going to were performed at conditions where we knew that defects would be formed. And then forces were measured with a 3-axis force dynamometer placed below the workpiece, and then optical metrology system was used to optically look and measure the size of the discontinuities. So here the force signature of a good weld, blue line is the estimated line and red line is the measured line. Now let us not get fooled by the fact that those two signals are overlapping very well, because that's the job of the discontinuity observer. Control theory based observer is trying forcibly to make those signals match. However, the outcome of the observer is the size of the discontinuity, which is what we are interested in. If it tells us there is no defect which is formed, or if it is formed, what's the size of the defect. So yes, this slide here essentially shows that whatever way my initial signal for good weld distorts, observer is able to keep up with that. So that's good news. Now, how about the size of the discontinuity which is being detected by the observer? For the good weld, we could not see any defect. For bad welds, we could see small defects. And again, a group of small scattered defects were observed in the third weld. And here we can see that the size of the discontinuities are really over predicted by the observer, which is expected given the very crude nature of the observer. So there are two things here. First, how the size of the discontinuities and the formation of discontinuities is related to the forces needs to be better understood. That's the next phase of the project, and we'll look at all of that right now. We got into. And then the second thing is, we actually are measuring discontinuities in 2D. We are getting an image from the optical macrograph, getting the area, but the discontinuity observer gives me estimates in millimeter cube. So I am doing a length scale correction, which again I am not sure of how correct it is. So I need a better way of measuring these discontinuities so that I can get a 3D estimation, millimeter cubes, void size in volume itself. So in order to achieve those two targets, we established a new weld setup where we coupled an encoder to the tool spindle so that we could track the evolution of forces with each degree rotation of the tool, FS tool, during the process. And then in order to get the 3D estimation of the defect size, we reverted to computed tomography, X-ray based computed tomography. So once the data was collected, one thing to be noted is dynamometer is placed below the workpiece, and therefore it is looking at the forces which are experienced by the workpiece. On the other hand, encoder is taking care of or looking at the angular rotation of the tool. So we had to get the forces established in the tool coordinate system, which is rotating coordinate system. So we performed a coordinate transformation such that the forces which are measured in the workpiece coordinate system are applicable to the tool. One thing to be kept in mind, we were performing experiments with tools with different number of flats on it, and therefore the 0 degree had to be established. So for each tool, one particular flat was designated as the initial flat, and that was butted against the flat surface of the lateral surface of the plate to establish the 0 plane of the tool itself. Finally, oscillating component of the forces were considered for analysis, because that's what tells us gives us the information about the periodic nature of the material movement. Some more experiments were performed at different conditions with tools, with 3 different tools with 1, 2, and 3 flats, and then went ahead and started looking at the forces as a function of the tool rotation itself. So here what we could find, I'm going to overlap the plots for all 4 different welds. Please notice all these welds were performed with different flats, and here we can see all the 4 signatures look very similar. Yes, there is a little bit of phase lag and there is a change in amplitude, and this tells us very clearly how the forces are playing or how the material movement is connected to the forces. So here we have plotted Fx. X is the direction perpendicular to the motion of the tool travel direction, and X forces are primarily responsible for the shearing of the material. So as the material comes into the stir zone, it gets severely sheared as it moves from leading edge to the retreating side. And retreating side is the side where the tool rotation direction and the tool travel direction oppose each other since the tool is rotating, and advancing side is the side where tool travel direction and the tool rotation direction are same. So material comes in at the leading edge, moves to retreating side, undergoes heavy shearing. Once it is plasticized, it becomes much easier to flow and it keeps the forces start to reduce. As the material reaches advancing side, forces again start to see a increase, and this is primarily because material is now getting pushed against the material which is already present in the advancing side. So moving for, yep.
Have you correlated the phase difference between the welds to the travel speed of the RPM or a combination of So what I mean is, if I look at weld 3 and weld 4, weld 3 is green. Right?
Weld 3 is green and weld 4 is black, yeah.
The amplitude of the force is almost 2.5 times.
Right, so you are right. Here the amplitude is a function of the advance per revolution. Advance per revolution is actually the ratio of the two parameters you just said, i.e. RPM upon the travel speed. So per revolution, if the amount of material which is present in the stir zone is smaller, it takes less forces to shear it or to move it around. So for weld number 4, for example, if I go back to the, I don't have to go back anywhere, you can see the ratios tell you that APR would be really small.
And why is the phase lag being used?
That varies from weld to weld slightly, have not investigated that particularly. First, the phase lag can be function of multiple things. One thing itself is the formation of discontinuities. Only the last weld here does not give discontinuities. First 3 welds give discontinuities. One thing very interesting to note here is you do not see the distortions in the sinusoidal signature in tool coordinate system, but you only see them in the workpiece coordinate system. So in order to do the transformation, fx and fy get connected to each other via sin theta and cos theta terms, and those terms, if you compute, give you a full sinusoid, again regenerate a sinusoid. Now the effect of defects and how these terms are getting combined can introduce the phase lag.
Then have you filtered the data? Because I would imagine the dynamo data to be very noisy.
So dynamo data was not filtered afterwards.
In this plot, are they filtered? Because sometimes, depending on what filter you choose,
you can get a lag and lead or lag. Correct. Right. So there was no additional filtering which was introduced in these. So this was a completely separate setup which I developed later on. And here we went to a NI card which had sampling frequency of up to 1 megahertz. So sampling frequency was very, very high, and it had a built-in filter feature which introduced lag or leads, if I remember right, to the order of nanoseconds.
I mean, if it's an inbuilt, then it is consistent throughout.
Exactly. So it takes care of any such lead and lag, the card itself. So there was no need to do any post filtration at the lab view or at any interface which we were using at that end. Okay. So moving forward, a similar force signature analysis was performed in the tool movement direction Fy as well, and we could very clearly see a clear trend across all the welds, where as the material is coming in the tool travel direction, it gets squeezed between the tool which is moving forward and the plate which is still in the place, and it sees a lot of compressive forces which are negative in number. As the material moves around the tool, these compressive forces relax down. Again, at the end you see there is a lot of rise in the tensile forces, or by tensile forces I mean the forces have changed signature. They have gone from compressive negative to a positive, which should correspond to tensile here, which is very interesting. Why? Because this again in some sense mentions or reflects that there is a cavity which is formed at the rear of the tool. Imagine if there is no cavity and there is a lot of material present at the back of the tool. Now the material which is moved by the pin has to push against the material which is present at the rear end of the tool. And what's that going to do? That is, will end up increasing these compressive forces rather than taking them in the positive side of the forces. So this again reflects the thought, or the hypothesis, bolsters the hypothesis that there is a defect, there is a cavity which forms once per revolution and gets filled in the process. Moving forward, looking at the CT scan images, some interesting images here. This was the case, the fourth weld, where no defect was formed, which was performed at the known parameters where no defects are formed. And these are the cases where you could see the defects which are formed on the advancing side in all the cases. Now, one thing which these images reveal very clearly, one common defect is a tunnel defect, or a continuous tunnel defect which is forming on the advancing side. These images clearly show that it's not a continuous tunnel. This tunnel forms in a very discontinuous fashion, one revolution at a time. You can see that with every revolution there is a chunk of material which is coming in. However, it has not been able to move all the way up to the end of the advancing side, and hence leaves a empty space, leaves the cavity unfilled at the area somewhere in between trailing edge to the advancing side. Another very good feature which can be observed here is that the front edge of most of these arcs, uniformly spaced arcs, are very continuous arcs. This is because at this end material is sticking with the tool pin itself as it is being moved by the tool pin. Then at different locations I measured the distances between these successive arcs, and it could be seen that the numbers are very close to the advance per revolution, which is the ratio of the travel speed to the tool revolution frequency, RPM. So once we understood a little bit how these defects are formed, what's the nature of the defects and how they are influencing the forces, we performed two different sets of experiments such that all the experiments in this table were known to produce no defects. On the other hand, all the selection of RPM and feed rates was done in such a way that we knew that defects are going to be formed of different sizes once these welds were performed. So for every weld, like the previous case, we made a specimen, defined at a fixed distance from the end of the weld, a region of interest. For this region of interest, we looked at the size of the defects which are formed, volumetric size in millimeters cube. And then we also got the force signature corresponding to each of these ROIs and performed the FFT analysis. But this time we looked at lot more different parameters, a lot more different matrices, not just only what's happening at the fundamental frequency. So lot of data here for different APRs. For each APR there were 5 welds which were performed, and for each weld, y-axis is the average force here. In this case, y-axis is the first harmonic, what's the force magnitude at the fundamental tool rotation frequency, second harmonic, third harmonic, and I went up till fifth harmonic actually. And on the x-axis we have void volume which is formed per revolution, which was measured from the CT scan data. Now one interesting thing which I was expecting to see some sort of strong trend here in the third harmonic, because all of these welds were performed with a 3-flat tool, and I knew that there are defects which are formed in all of these. However, not a strong trend is seen. The magnitude is pretty high. However, if you look at the second harmonic, the magnitudes here are of at least twice the size of the second harmonic for any given case. However, I don't see the trend I was looking at. So I started looking at the different combinations of these harmonics, harmonics and average forces, and that is where third harmonic normalized by the average force tends to give a pretty neat trend. The data points start to fall in a linear sense with very comparative slopes. Now, this helps us out to the extent where I want to say what's the size of the discontinuities form, assuming this relationship applies for most of the tool geometries. So all that data is here. One problem was that the same parametric third harmonic normalized by the average force have very similar magnitude for the welds which were formed at the conditions known to produce no defects, for all the good defects. So how to differentiate between a good weld and a bad weld? How to say when the defect is formed and when it is not formed? So again, when I was looking at different combinations of those force parameters, the ratio of third harmonic against the first harmonic clearly creates a divide between the welds with defects and without defects. There is a big gap here, and this is where pick the value of 0.02, 1/10 of the size of the minimum normalized force observed where defects were, for which the defects were observed. And with this critical value, we developed an algorithm saying if this ratio is more than 0.2, a defect is formed. And if it is formed, then applied this linear correlation. There is some spread to it, I agree with that. However, it does follow a very clear trend. And finally, know if no defect is formed. So finally, for validation, bunch of welds were performed at different RPMs and feed with 3 flat tools, and then one weld was also performed with a tool which had 2 flats on it. And for no defects case, the algorithm predicted the same, welds with no defects. On the other hand, for the cases where defects were formed, well, not only just the algorithm developed not only clearly identified that discontinuities are formed, it also mentioned that it's worthwhile mentioning that percentage errors were pretty low. Previously, we were over predicting with the crude methodology developed by a factor of 20, 27. Then with the help of the observer approach, which was developed previously, applied the same algorithm to the observer in real time, and we can see as the defects are formed. So for this particular weld, we identified in the CT scan a lot of regions of interest, ROIs, corresponding to the width of 1 APR, 1 advance per revolution. And what I observed, or what we could see, is that the predicted size of the defect as the weld is happening could be captured decently well with the proposed algorithm. Now, in this very interesting weld, what I tried to do, I wanted to see how the transition occurs. This model has some strengths, but then one of the weaknesses which is revealed in this interesting case was, in this weld, I performed a transition weld where at half length of the weld changed the weld conditions. So from 900 RPM, 500 millimeter per minute, the CNC program, I changed the weld conditions to 1000 RPM and 600 millimeters per minute. And we could see that due to the sudden acceleration or deceleration or sudden acceleration in the tool RPM, there is additional dynamics involved, which is definitely not the part of the algorithm which is developed, and hence algorithm does not do a very good job of capturing how the defects evolve over that transition period. However, as soon as the process settles down, the algorithm catches back and does a pretty decent job of again tracking the defects, the size of the defect which is formed once per revolution. So with that, with any experimental work, it's a necessity to get into the uncertainty and any limitations of a proposed method or model. So uncertainty wise, the order of the force harmonics, the normalized force harmonics was at least an order higher than the order involved, than the order of the uncertainty involved with the DAC which was used to do the measurements. Similarly, for the CT scan, the size of the defects which were measured were at least 3 to 4 orders larger than the size of the voxel which was used to measure those defects. Further, this is a very interesting case. This weld was formed with a tool which had only 1 flat on it. Now we have seen that additional harmonic is observed at additional force dynamics is observed at a harmonic corresponding to the number of flats. What happens if there is only 1 flat? Then the additional dynamics is happening at the same is happening at the same frequency as the tool rotation frequency. That can be in phase or out of phase. And if we go by the earlier model where we said that the forces are proportional to the size of the material moving around the pin, and with defect the amount of material moving around the pin reduces, we should see a severe reduction in the forces at the fundamental harmonic or tool rotation frequency. So this is the FFT for weld where performed with one tool flat where defects were formed, and we do not see much activity or any activity honestly at the tool rotation frequency or at the fundamental harmonic. So one limitation of such a method is we can only use this method for, or methodology proposed for friction stir welds which are performed with tools with 2 or more flats on them. So to wrap up the talk, bunch of points to be summarized, concluding remarks. Forces are inherently tied very closely to the material movement. The cyclic nature or periodicity of the material movement very clearly reflects in the periodicity of the forces, and hence force signatures can be used for measuring or detecting the formation of defects during the welds. Now the additional harmonics which is observed has been exploited in the proposed method. The additional harmonics, I mean the additional force dynamics which is observed at the tool rotation frequency corresponding to the nth multiple of the tool rotation frequency, higher harmonic corresponding to the nth multiple of the tool rotation frequency, where n is the number of flats. So another indirect outcome of this work is that we can have tool design particularly which can help us detect the defects. If we know the flats, or we can choose the number of flats in a way which will help us set up better observers to detect defects which are being formed. So most of the time tool design optimization is done, those exercises are done in order to get right temperatures during the process, to get right grain refinement during the process, to get enough plasticization or getting reduction in the flow stresses during the process. But then an additional input can be brought in based on this work where we can have number of tools for which a control theory based observer can be set, number of flats on the tool for which we can have observer which would allow us to detect defects during the process. And then the last 2 bullets on the slide basically emphasize how the normalized forces, not just the forces any one particular metric gives us a good detection of the defects. With that, most of the bulk of this work was performed in medicine during my doctoral work. So I must acknowledge all the advisors, lab mates, one of which is here, and a lot of other people, including Amit himself, have been citing his work for a while now. Thank you. I would love to take any questions and discuss it further.